Okay. Okay, thank you. I'll try to cover briefly and superficially two topics. Both of them are, the goal is to develop eventually a theory, statistical mechanics based theory of cognition or intelligence in brains and machines. So the first topic is going to focus on our work on object representations. Interpretability, it was a theme that we discussed yesterday to some extent. So here's, I want to outline an example of how we go about understanding the representations of objects, in this case, in convolutional networks and in brains. And so this will be the first topic. This is not going to be learning. It's going to be looking at the solution of in this case, let's say, object categorizations emerging in deep convolutional networks, trying to capture the properties at the population level and geometry in high dimensions, and as a tool also eventually to compare representations of the same data in convolutional networks, different networks, and also networks versus the brain. And I'll show you a glimpse of an attempt also to compare not only between different systems in a visual domain, but also representations of vision and language. So this will be very brief. The basic idea is to capture the geometry of manifolds as they evolve from the input pixel layers to the top feature layers, both in sensory hierarchy, in this case in vision, and in deep convolutional networks. And what I mean by manifold is simply the set of states in a given stage and a given layer of the network or the neural system that correspond to the representation of many instances or images of the same category, maybe the same person or the same object. So this is what I mean by manifold. And the basic idea is that those manifolds are very distorted and overlapping in the input layers, so they are not linearly separable. But as this data is being formatted or propagated across the layers, and you look at the top layers, then each manifold corresponding, for instance, in this case, to different persons are being well separated or untangled. So the question is how to capture the geometry of neural manifolds in a given layer of processing. And just give you a highlight of the idea. The idea is, again, here we have different object in a given, this is again a representation, a state space of a given stage, a given layer of neurons. So n is the number of neurons in that stage. Each point is a response to a given image. Each manifold corresponds to all images, let's say, of a cat. This is manifold of all images of a house, a car, and so on, a dog. The theory, in this case, statistical and mechanical theory, captures the conditions under which this manifold can be linearly separated. By linearly separated, we mean technically we just randomly label each manifold by plus or minus 1, and we ask whether a hyperplane in this state space can separate all the plus 1 manifolds from the minus 1 manifold as shown here. And this is a useful tool, computational tool, because it gives us a capacity notion of the object representation. By capacity, I mean we can now measure analytically, theoretically, calculate and measure numerically how many manifolds in a given stage of processing can be linearly separated per number, per dimensionality per n. So P will be the number of manifolds that are linearly separable, N will be the number of neurons, and basically the theory is that under some randomness assumptions, we can take the thermodynamic limit, and that's an important concept for statistical mechanic theory. We take the limit where the number of neurons or the width of the layer goes to infinity. The number of manifold in this representation also diverge, but the ratio between them alpha is finite. And then we can ask what is the largest alpha for which a hyperplane exists that separates the manifolds plus ones from minus ones, and the geometry is fixed. So, yes?
How are the manifolds defined? How do you define the manifold?
Yeah, I skipped the precise definition, but the manifold is here simply defined as a collection of points, can be infinite, can be finite, in some linearly low dimensional. Each manifold is d-dimension, which is much lower than the size of the entire embedding representation. There is no smoothness assumption here, just a collection of points.
So my question is, given n neurons, how do you define the manifold? The ones that are active?
How
do you define the manifold? The neurons that are active at a given time for given presentation?
Each image, each input generate a vector of responses. All the neurons.
Of all the neurons?
It's just a collection of vectors.
Okay,
here.
got it.
I
understand.
This is here. Okay? Each point here, let's say this point, is the vector of responses of all neurons to this image.
Understood.
Okay? That's it. Okay, so this gives us the notion of capacity, which we can calculate analytically, and the notion of geometry of manifold that's associated with it. In other words, how this capacity depends on the shape of the manifold, the smoothness, the extent, how many dimensions. So this is the notion of effective dimension and effective radius, which I won't go into it. It's all published. But I just bring this to give you an example of how we use this measure to compare representations of the same data in artificial networks and in the brain. So this is an example of data from a few hundred neurons in IT cortex of a monkey. Again, in response to about 30 different images, corresponding to different people. Each one of them is about 8 different poses. So you can think about this now as a manifold consisting of 8 points, but now we have about 30 manifolds of this type. Just as an example. So again, a manifold will be the vector, each point in the manifold will be a vector of dual responses in a given a patch of IT cortex selective for faces. So this will be, each image will be one vector. This will be a manifold of 8 such vectors, and then it will be 30 manifolds of this type. And we can ask how these manifolds are spread. Are they compact? In other words, whether these manifolds are more than just random collection of 30 by 8 vectors. So we can then, so this one I just want to show you how we think about this. So we measure the capacity of separating those manifolds, again, per neuron. So this is this measure here, in convolutional networks, VGG faces, which have been trained to do a face recognition task. And this is the capacity as a function of the layer. So this is the pixel layer and convolutional layers up to the feature layers. So the capacity is kind of hanging around and then increases to a value close to 0.4 something at the top layers. Now, remarkably, this value of capacity is very close to the capacity of separating the same manifolds in IT cortex. Okay, so this is this dashed line. And that's not an accident, because if we propagate the same data by taking it through a network, again, trained network, that has been trained for object recognition. The same architecture, VGG, but it's VGG16, which just has been trained for general object in image and task, okay? And this is the capacity we get, okay? So now, there is no free parameter here. There is no fitting parameters. It's just, we propagate the same data, we get a number, and we compare this number to different artificial networks. So I think this is the remarkable, in my view, beauty of these tools, how we use artificial networks and theory to to try to make sense of the nature of representations of object faces and so on and so forth.
Yeah, I noticed something interesting. So all the previous layer except for the last two are convolution plus.
Right.
Okay, so why does the capacity just suddenly increase?
There's a whole lecture about that. There's the geometry here, correlations. This will be a whole lecture. And I just don't want to show you just a snapshot of what is the output of such an analysis, of such a paradigm. Okay? Good. So I'll answer questions later on. I want just to give you another snapshot, just a pointer. This, we study a lot of this type of questions in vision, but we also ask, is there something common in representations of the same concept in a language network versus a vision network? And we do it by what's called zero-shot learning, which is the following thing. We take again, concepts, let's say animals. We have the images, of course, and you have also linguistic descriptors of them. Okay, so this is data that we take from ImageNet data set. So, Croati is described by a linguistic, by a phrase of language and non-but and so on. And now what we do is we take an artificial deep convolutional network, has been trained to do object categorization, but have never seen this concept, this object, this type of animals. So it's a new concept, a new category. So now we ask, can we present an image of one of these categories to the network, propagate it, get the response at the top layer, and decide whether it is Croati or number, whether these two categories were never been seen in the training of the network. So how do we do it? We take the corresponding word embedding or language embedding of these two categories, because the language knows about these categories. We form the representation of these categories in the language, and we map them. We find a mapping between representations of objects in language space to representation of objects in the vision space. We do the mapping using the train concept, because there we have the object representations that the network has seen during training, and we can do mapping. And turns out this mapping is simply a rotation. So then we use to freeze this mapping, and then take these vectors from the language embedding, use this mapping to get the vector representation in the vision space. And then we look at which a given image, to which vector it closest. And what we get, so this is the cartoon, and what we get is amazing success of this zero-shot learning, about 98% accuracy. So again, it's accuracy of categorizing a new image corresponding to new categories that the vision network has never been trained for, using knowledge or geometry of representation of these new categories in the language space. And to me, this is remarkable that this type of process really succeeds, because it really means that there is some underlying commonality, not only looking at the same visual space in different networks and networks in the brain, but also across modalities. Okay, so this is just snapshots of the type of work that we do, trying to use AI, deep convolutional networks, plus statistical mechanics theory to understand better the brain. And now I want to switch to my second part of this brief talk, and this is about statistical mechanics of deep learning. Not about the representation of trained network, but trying to push the understanding of statistical mechanics of the learning itself. And many questions, capacity, generalization, and so on and so forth. This is work done with Qian Yi, a Harvard student. First was mentored by the first speaker this morning. And so here's the idea. We have a supervised learning of fully connected deep neural network. So this is here. We have input layer, W1, W2, the hidden weights, and then a readout weights, a linear output. And we're using mean square error as the measure of the loss. So F is the actual output of the network for a given input X. So this is Fx. Theta is the network parameters. Because the output is linear, is simply given by AI dotted with the phi I. Phi I are the activation in the top layer, okay, X and W. So A is the readout weights, W is a collection of all the weights in the hidden layers. Okay, so we have this loss, which is the distortion between the predictor, the network output for a given training data, X, and the label, Y. Okay, so this is the classical, conventional, empirical loss measure of the goodness of a particular set of parameters, theta, for given data. Now we're using statistical mechanics formulation of the process. We're saying we are not in this work. We're not studying the dynamics of the learning itself, but we're saying whatever the dynamic is, graded descent, genetic algorithm, whatever you choose, we are assuming you get some loss after training, and we are interested in kind of a Bayesian approach, where we are asking what is the posterior distribution after learning of the weights of the network after it had been trained on a given set of data. Okay, so this is this part. Temperature is this coefficient here. So the lower the temperature is, the more we are constrained on a region of space, a state space. State space now is the weight space that are solving this task. Okay, so this is the empirical loss, and an important regularizer, which has already been mentioned here, is an L2 regularizer with a coefficient sigma square, which is favoring weights which are smaller in magnitude. Okay, so this is a kind of a very natural statistical mechanics approach to a framework to understanding the outcome of supervised learning in a feed-forward network. And particularly, already has been mentioned here, what is interesting is the overparameterized regime, where the network is so huge that it can easily find solutions to all the training data. So F is precisely Y for a range of parameters. So this is captured here. So imagine there is a whole region of phase space, a flat space, state space, where the error is actually zero. The training error is zero. And then what this framework is doing is telling us what is the statistics of all the weight vectors, all the set of parameters that are consistent, fully consistent with the training data. What is the generalization properties of them, et cetera, et cetera. Okay? So this is the zero temperature limit. Overparameterized regime, easily solving the data, the training data, to get zero error and asking what is the generalization properties of those. Okay? So the goal here is to understand the structure of the space of solutions and how the structure affects generalization. And now we talk about generalization. So the idea is we take, after training, we take the output of the network, F, on a given test point, we compare it to the desired label, and we have a measure of generalization, okay? So already I see that I'm very close to ending. I must end, but let me just give you a highlight of what's going on here. So what you can easily do is integrate out the readout weights, because the problem is linear on the readout weights, and you get an effective Hamiltonian on the other weight. So this is given here, and it turns out that important that the actual effective Hamiltonian on the weights are controlled by a kernel function, which is the dot product, the similarity matrix on all the training data of the top layer of the representation. So this is this dot product between the same vector of nodes responding to a pair of inputs x and x prime for a given w. So this is the kernel function. So everything really depends on the properties of the kernel function and the relation between the kernel. The kernel is a function of the data x and x prime given w and the labels y. Okay, so this is the goal of theory, is actually to unpack what is the properties, the statistical properties of the kernel matrix. So it's P by P matrix, well defined. Now the problem is that this matrix is a function of all the parameters W, because it is a function of the representation of the top layer, which is read out by A. Okay, and the whole problem is that this is a highly nonlinear function of the kernel. The kernel is a nonlinear function of W. So the entire theory, in my view, goal of my view, is to actually understand the structure, the statistical structure of the kernel. How do we average over the kernel, and so on and so forth. So it's well known that there is a GP limit, Gaussian process limit, which is the limit where there is the number of training samples P, the dimensionality of the kernel matrix is fixed, and the width goes to infinity. It's well known and studied, and beautiful work on it. The problem is that it's not an interesting, in many cases, not an interesting limit, because in that limit, the weights are Gaussian. So it basically says you have a deep network, you have millions of parameters, but most of them simply Gaussian sampled, and only the readout weights are really learned. Okay, and so that's obviously not a realistic limit. So how you go beyond that Gaussian process limit? And basically, the limit that we are focusing on is the limit, as in the first part of my talk, is where the width of the network goes to infinity, but also the size of the data points goes to infinity, but the ratio P over N is fine. This is the classical statistical mechanics limit or framework in neural networks from the beginning, so to say, in the 80s. So we have a width parameter, which is alpha. In the Gaussian process limit, alpha is 0. And we're interested in finite alpha. Alpha can be, in our case, can be even infinite. So there is a very dense packing of training points, of training data on the width of the network. There is depth parameter L, and so on and so forth. So I just want to show you, so how do we go about this? So it turns out that in certain networks, particularly in linear networks, but in also some nonlinear networks, there is a beautiful structure of how the kernel is unpacking when you integrate out the weights. So I showed you that if you integrate out the readout weights, the effective Hamiltonian on the rest of the weight is given by this kernel, which is a function of all the weights. It turns out that for linear networks and some other networks, similarly, if you integrate out the top layer weight W, you again get the same Hamiltonian structure, but now as a function of the remaining weights, but the kernels are normalized, are scaled by a scalar U, which is the order parameter which emerges from integrating out those weights. So this is an amazing simplification, that you start from a very complicated effective Hamiltonian given here with the kernel function, and you end up with a free energy after you integrate out all the weights, which is given by the input kernel, because now you integrated all the weights, so it's just the input kernel scaled by the kernel is simply scaled by a renormalization, which is called the kernel renormalization order parameter, which is computed self-consistently. So we use here notion of statistical mechanics and renormalization group, and use the modular, the layer structure of the deep network to actually solve the problem piece by piece, like we do in renormalization group, until we end up integrating out all degrees of freedom. And in this way, we get a very elegant theory that tells us that you can use the kernel, the input kernel, and the integration of the W's from the top kernel to the input kernel simply ends up scaling the input kernel by this self-consistently determined order parameter U. And this works beautifully. This is an example of the generalization error computed with our theory. This is the numerics. This is the theory. And this is the GP limit. The GP limit is n goes to infinity, so there is no width. So this is this value here. And this is a realistic finite width network. And you see that in some cases, the generalization error actually goes down with n, which means that the more parameters you put for a fixed size of data, for fixed data, the better you are in generalization. So this is the over-parameterization case. Here is the opposite example, depending on the level of regularization, where actually you are over-parameterizing, you are actually overfitting the problem, and generalization error goes up. So this is one example of many similar examples that show that statements about it's good to over-parameterize, it's bad to over-parameterize, it's good to be in deeper network, or it goes or not, they are all correct or all incorrect statements simultaneously, because it really depends on other parameter. Regularization parameter, for instance, is a very important parameter, meta-parameter, that determines many aspects of the system behavior, depth, and so on and so forth. Anyway, I think I have to stop. I just want to mention that renormalization comes in flavors. I showed an example of a scalar renormalization. In the case the network has multiple outputs, the input kernel is renormalized not by a scalar, by a matrix, which corresponds to the dot product between pairs of outputs of the network. And also more recently, we're studying a new type classes of nonlinear networks called gating networks, which have many beautiful parameters, beautiful properties, but they can be exactly solved using the renormalization of the kernel idea using statistical mechanics. So I'll stop here.
Thank you very much. That was a wonderful talk. I just have a question that basically, just to start, I can see on the linear networks, maybe other networks, where this renormalization group idea works, but is that the general feature for networks, or are there some networks where this just renormalization is not a good approximation for it?
Can I use this?
Yes.
So the renormalization works for the cases where work for the cases where the full structure of the problem can be explained by a kernel matrix properly normalized. The normalization may be complex, but we suspect that in general nonlinear networks, the theory relies, the properties of the system rely on other statistics. Kernel is, you can think about it as a second moment statistics of the representations, but in other cases you have to go to fourth order and so on. So in another line of work, we and others are developing a kind of a perturbation 1/n theory, where we try to capture the contribution from this kind of 5⁴ order terms in the Hamiltonian.
It will be interesting to see how far you can go without in the perturbation.